do eigenvectors form a basis? We are going to have eigenspaces, and thus we are going to have eigenvectors. Do they form a basis? So, tell me how many stretchings we can find so that we can make the stretch columns aligned. What am I showing you here? I'm showing A1, A2. I'm showing you a matrix that looks like 3, 1, 0, 3. True? And I'm asking you how many stretchings, that means those lambdas, you can find so that we can make the stretch columns aligned. That means how many different eigenvalues am I asking? Is it clear the question that this question here is actually asking you how many eigenvalues do we find? How many eigenvalues do we find? 1. That is 3. True? If you do this one go up to 3, this one goes here. True? If I shrink this one, I have 3 minus lambda, 0, 1, 3 minus lambda, true? And I need to find the lambda, for that, I've got determinant of that stuff equal to 0, true? Are we together? Perfect. 1, 2, they are not aligned. 3, whenever I put lambda equals to 3, what do I get? 0. I get this one is here, and this one is here, true? You say that you find only one. Perfect. Now, this plot here, I should have checked. How do I find the eigenvalues? The eigenvectors. I need to find the kernel of this stuff, true? What is the kernel of this stuff here? One, zero, true? The kernel of this stuff is this one. This is my eigenspace associated to lambda equals to 3. Are we together? Are you going to be able to find other eigenspaces? No, I got only 3. Or better, 3 is the unique eigenvalue. That is the kernel associated to that modified matrix. How many dimensions does this one span? 1. True? How many eigenvectors would I need to find a basis of R2? At least 2 linearly independent. True? Are you able to find 2 linearly independent eigenvectors in this situation? No. Are we together? Can we, in general, say that eigenvectors form a basis? No. Whenever I have some stretchings that look like those ones, whenever I've got A's that look like this one, I'm not able to find a basis of eigenvectors. How much are we together, people? Perfect. So,
sorry.
Question.
The shape you told is like upper triangular or also other shapes?
Also this one.
Hello.
Or also something like this. We are going to see, we are going to investigate very much better up to now. So we do not having, we are not in general guaranteed to have a basis of eigenvectors. Together on this, I think so. Perfect. Let's tell me this. Go look at this question here. This question here is actually very easy. Go read, discuss, and try to solve. Am I recording? I hope so. This is kernel, sorry. This null space is kernel. People, what would you say? What would you say, people? You will say number. I would like everybody to answer. If you do not know, put I do not know, people. It's very important for me. Okay, let's go one by one. This one, what does it say? We have a 2 times 2 real matrix A with eigenvalue lambda. If lambda is an eigenvalue, can this one happen? No. If lambda is an eigenvalue, it means that A minus lambda I is rank deficient. True? It's the definition of eigenvalue. True? It's not the definition of eigenvalue, but it's in a certain sense following directly from the definition. So this one cannot be. This would indicate that lambda is not even an eigenvalue. Are we together on this? Are we together on this? That is very wrong. Okay? This one, what does it say? It's the same. It's the same of 1. Are we together that 3 and 1 are the same, are saying the same thingy? Perfect. What does 2 say? The dimension of the kernel is 2. It means that the kernel of this stuff here has at least 2 linearly independent objects inside. True? But every v that is in the kernel of this matrix here is an eigenvector. The fact that the dimension of the kernel of this modified matrix is 2 means that I can choose 2 linearly independent eigenvectors. It means I'm able to find a basis. How much are we together, people? Questions? Questions? I see some twos. There must be some question. You might ask me later then.